let's go into the APIs. Okay, remember these are the functions that help you to do some of these memory management and all those things more easily. So these APIs are extensions to NCC programming language, and in fact, they are more or less GPU versions of the C, API functions like malloc kind of things. But there are also data transfer API functions that make your life a lot easier when you need to transfer data between the CPU and the GPU. And the hardware is actually designed in such a way that these API functions can run very efficiently, okay, underneath, the implementation underneath. So let me we're going to be using a very simple data structure to illustrate a lot of these concepts. So I'm going to introduce this data type. This is just a C data type, okay? There's nothing fancy about this data type. It's a struct. It has width, height, and pitch, okay? So three integer fields, and then one pointer field that points to the elements. So this is a matrix data type. The width and height is intuitive, right? The width of the data structure and the height of the data is a two-dimensional matrix. Fine. The pitch means that this matrix may be a part of a bigger matrix. Okay, so if you have a bigger matrix and the particular matrix that you're trying to represent here is only a part of it, then you have a little bit of an issue. The issue is, if you look at the bigger data structure and you look at a smaller data structure, in order for me to access two consecutive rows, I can't really just move my pointer easily to the beginning of next row, because in reality the memory layout is such a way that I need to actually move past all the remaining parts of the bigger data structure in order for me to get to the next row. So this is the dimension of the bigger data structure is called pitch. So I know how to move my pointer from the end of the current row to the beginning of the next row. I need to know that piece of information. That's pitch. Make sense? Okay. So that's the data structure. Okay, and I'm going to use this data structure for quite a few things here. The first API function I'm going to talk about is the Cuda device memory allocation. Lowercase Cuda, capital M, alloc. And this is a function call that allows you to allocate memory objects in the global memory. Okay? And it requires two parameters. One is the address of the pointer to the allocated object. Okay? So the function is going to come back with the address in that pointer, right? That pointer value back to you. So you need to give the address of the pointer so that it's a call by reference, and the function will put the pointer into that address and return it to you. And the second one is the size of, which is essentially the number of bytes that you want to allocate with the Cuda malloc. You also have the Cuda free, which will free the object from the device global memory, and obviously it's going to be the pointer to the object that you're going to free, right? So this is how you allocate memory in the global memory on the device side. So one code example, let's say I want to allocate 64 by 64 matrix in the GPU, right, in the device memory. Okay. So what and I would attach the allocated storage to the MB element. Usually the convention is M will be the name of the data structure, and you attach a little D to it so that you know that it's the device version. Oftentimes you have shadow data structures between the CPU and the GPU, and you use the letter D to mark the version that is going to be the GPU so that you don't get confused. And so you will say, okay, I'm going to have block size 64. I'm going to have 64 elements on each side. And I'm going to declare matrix MD as a matrix. So you will allocate that little struct, right, that I just talked about. And so this is a static allocation. And then I will calculate the size to be block size times the size of the float, single precision floating point. So this gives me 64 times 64 times 4 on most of the architectures today. And so that's the total amount of bytes that I'm going to allocate. Then I call Cuda malloc. And I'm going to be passing the address of the pointer that will eventually point to the allocated data structure, and I give it the size. Okay, so after the function call, I will have a pointer that points to the data structure in this particular struct, right? And I could also free it by just passing that pointer to the free routine. Okay? Easy enough. This is very similar to C, so it should be fairly quick, right? There's a Cuda mem copy. So this is similar to the C mem copy routine where you used to copy memory around in C programs. But this function actually allows you to do data transfer host to device, device to host, host to host, device to device. Okay, you can have 4 different modes of using this function. And it requires 4 parameters. You need to know where the source is. Okay, you need to have a pointer to where the source data structure is, right? And you need to know where you're going to put it, right? You need to have a pointer to the destination, right? Obvious. You need to know the number of bytes you're going to copy, right? Easy, right? And you also need to know the type of the transfer. You need to know whether you're transferring from host to device or device to host and so on. So one code example, if I want to transfer a 64 by 64 single precision floating point array, I would just remember that size is assigned 64 by 64 by 4, right? So that size variable gets passed in. And let's say M is in the CPU memory that contains the original data structure, okay? The user data structure that you start with. So you will need to put, have the pointer, let's say, host to device and device to host. So this is the source and this is the destination. And then the source will be pointing to the M elements and the destination will be the pointer that you just allocated. Remember, you allocated a piece of memory in the device memory, and this is how you fill that device memory. So you pass the address or the pointer to that device memory area, and then you copy all the data in there. This particular constant will be translated into a numerical number that indicates that you will be doing memory copy from host to device. This is just a little bit easier to remember and harder to make mistakes. You also can do, memory copy from device to host. So essentially you reverse the 2 pointers and use a different constant that will allow you to copy the data back into the CPU memory. Okay? So these are the very generic, very basic functionalities that you're going to be using. There is a table that you need to kind of remember, but usually you would remember it anyway after a couple of times. You can declare functions to be device, global, or a host. Okay? Remember, these are the deco specs that I talked about earlier. Whenever you declare a function to be device, it's underscore, I think it's underscore device, underscore, that means you execute only on the device, and it's only callable from the device. Okay? So if you mark a function as a device function, that function can only execute on the device, and it also can only be called from the device. The reason is the GPU has a different calling convention from the CPU. So you need to know, when you generate code, you need to know where you're going to be called from. So this simplifies the job. You're saying that these functions can only be used from the GPU and executed on the GPU. So they only need to generate a calling convention on the GPU for those functions. you can declare a function as global. And whenever you declare a function as global, it's one of those kernels. Okay, only kernel functions are global because only kernel functions can be called from the CPU, okay, and execute on the GPU. That's why it's global. It has to be visible from both ends. And these functions will be executed on the device and only callable from the host. You can also declare a function to be host. And that means that you can execute on the host and call on the host. However, if you have some functions that you want to have two versions, one for host, one for device, and you want to be able to, to use the same function on both ends, you can actually use both keywords in front of the function. You don't need to declare it twice. Just use both keywords in front of it, then the compiler will actually, remember that split? The compiler will send the function down both paths so that it will generate the proper versions for each path. Okay? And the global function can only return void. It cannot return a value, okay, to the caller. Device functions are somewhat limited, okay? You cannot do an indirect function call on the device. When you write a device program, you cannot just take the address of a function on the device and then say, okay, call to pointer. It doesn't work. The reason why it doesn't work has some implementation implications. It turns out that in order to calculate the resource requirement, the compiler needs to know exactly the call tree. That is, how the functions are invoked. So therefore, you cannot use indirect function calls, and also by this time, many of you should say that you cannot use recursion either, because recursion gives you a limited level of calls that can use up resource in a way that you cannot calculate. Okay? So no recursion, no static variable declarations inside the function. Whenever you have a device, let's say a parallel function, a parallel program with a static variable in these function calls, it's always problematic because now you need to figure out, which one shares the static variable and which ones should see it and how do you synchronize, and it becomes a mess. So no static variables inside the function. You can only have either totally global or totally local, and some of the shared memory explicitly declared across the threads in a block. You cannot have variable number of arguments, and that has to do with the stack implementation. The stack frames has to be fixed in this architecture in order to do what we call the practice stack. For those of you who are familiar with these parallel function calls, you need to have, essentially bounded stack frames so that you can generate parallel call stacks properly. And that eliminates variable number, args. That's the reason why you will not be able to call printf on the device, because printf is a very arg function call. Okay? However, if you use a emulation mode, you can actually use printf, and that will be clear in the NP assignments. Now, let's go into action here. When you have a function essentially operate on a massive data structure, okay, you will be writing a kernel function. And then you will be calling that kernel function in the following way. You will be calling that function with what we call the execution configuration. So this is actually a piece of CPU code, okay, that will be used to invoke a kernel. So you'll have essentially a declaration of the kernel function. Essentially this is a C header, the prototype, function prototype, and then you have what we call the theme3 data structures. And these data structures essentially give you the dimensions, okay, of the thread blocks and the threads that you're going to generate for that kernel. So in this case, what I'm saying is the grid has 2 dimensions of blocks. I'll have 100 by 50 blocks in my organization. And then each block is 3 dimensions. I'll have 4 by 8 by 8. So each block is a 3-dimensional, collection of threads, and that gives me 256 total. So when I'll declare the amount of shared memory that I'm going to use. And this is, in this case 64, but I have not taught you how to use shared memory. Okay, I'm just giving you a preview that you also need to specify the number of bytes you're going to use for that, for that kernel. So when you call the kernel function, you will have your ordinary parameters, okay? But between the parameters and the function name, you will have 3 less than signs, and you will get the dim grid, the dim block, and the shared memory bytes as configuration variables to the kernel. And the hardware is actually going to take these numbers and generate all the threads for you. Yes?
Why is the dim grid return, is it a dim 3 even though it's 2-dimensional?
I'm sorry? Whether
The dim grid, 100 by 50?
Yeah.
It's 2-dimensional?
Yeah.
Why is it a dim 3?
Okay. Yeah, that's a great question. It turns out that, instead of creating another data structure, you just use, dim3 actually will have 3 fields. You just not use the 3rd one. And the hardware knows that there are only up to 2 numbers. Okay. So it's not going to be confused. It's just pure declarations. Okay, so any call to a kernel function is asynchronous from Cuda 1.0 on. For those of you who have friends who took this course, Cuda used to have totally synchronous kernel calls. Whenever you call a kernel, the CPU stalls, okay, automatically.